Collision detection in games comes in two types: discrete and continuous. Discrete collision detection methods are used to solve whether two bodies are currently overlapping or intersecting. Continuous collision detection solves whether two bodies will collide based on their velocities. In this episode, we'll be implementing discrete collision detection, with continuous coming later. If you've been enjoying this series so far, consider triple smashing that like button, subscribe, and hit the bell so you don't miss future episodes. Before we get into the collision detection, we'll need to create a simple line rendering method that'll come in handy for visualizing our collisions. For this, we'll create two functions in the render module. In renderInternal.h, we'll define a new VAO and VBO for lines and fill out the init prototype. Now let's fill out the function in renderInit.c. We'll generate a VAO and VBO and bind them. Next, we'll use glBufferData, but instead of filling it with data, we're going to specify the size and pass null. We'll fill the buffer later. Also, set the last argument to dynamic draw. This hints to OpenGL that we'll be updating the data in this buffer frequently. Next, we'll define just one of the vertex attributes. We don't need the UVs, as we're just using a solid color. Finally, we'll unbind the buffers, and we're done. To render the lines, we'll head into render.h and define the function prototype. We'll call it renderLineSegment, and it takes a start, end, and color. While we're here, we'll define a couple of other required function prototypes: renderQuadLine and renderAABB. Copy the prototypes, jump into render.c, and paste. First, we'll fill out LineSegment. Start with using the default shader. Then we'll set GL line width to 3. This is done so that you can see the lines in the recording, and it's optional. Next, we'll set the coordinates as if they were offset from 0. Then we'll create a model and translate it to the starting coordinates. In our previous code, we used the matrix identity function explicitly, but if we look inside linmath.h, identity is actually called by translate, so we don't have to call both. The rest is pretty much the same as the quad rendering, but we'll use glBufferSubData to dynamically insert the vertices every frame. As well as that, we must use a different glDraw function, glDrawArrays. Moving on to renderQuadLine. This function will use the one we just created to draw a quad made from lines instead of a filled one. We could have just used a function called glPolygonMode to render in wireframe, but we'd still be rendering the diagonal lines of the triangles. In any case, we need 4 points, so let's define them. Then we'll just call renderLineSegment 4 times. With that done, we'll move on to renderAABB. For this one, the module doesn't know what an AABB is, so we'll just use a float pointer. We'll scale up the size and then render using QuadLine. In the renderInit function at the top, we'll call renderInitLine and also enable blending so that we can have transparency. Over in main.c, let's delete all the test code from last episode. Then we'll create a test AABB, set the position to the center of the screen, and the half size to 50. Now down in the main loop, we'll render it as white with a 50% opacity. Build and run the game, and we should have a quad drawn from lines in the center. In physics, we'll just define one function prototype for now. Point intersect AABB. It returns a boolean and takes a vec2 and an AABB. Copy the prototype to physics.c. But before implementing that function, we'll define another one here called AABB min-max. That's going to take two vec2s as pointers and an AABB and fill the min and max vectors. The reason we do this is because our AABBs are stored as the center point and half size, but for a lot of calculations we want to get the minimum and maximum position. Now in our intersect function, we'll define min-max, call AABB min-max, then just do a simple bounds check. Now we're going to head over to our util.h and define some colors to make life a bit easier. Back in main.c, go to the input handle function and delete the code for moving the box around. Next, create two temporary int32 variables, x and y, and call the SDL getMouseState function, passing their addresses in as arguments. We want to render a little dot on the cursor, so we'll update the pos vector to do that. Next, we'll want to hide the default mouse cursor on startup, so just call SDL showCursor and pass in false. Finally, we want to check if the cursor is intersecting with our test AABB, and if so, render a red quad. Otherwise, render a white quad.